When I walked into there, I didn't recognise Tony. When I knew him, he had a bit more hair and he was a bit slimmer. And then I realised he didn't recognise me either. I met somebody else. Now, I want to talk about lean product development. And lean is a word to me that covers many sins. And it's a word which is used quite extensively for manufacturing, for product development, for other bits and pieces. And when I think about it, when I was at Fisher & Paykel, most of my time was spent in manufacturing. And I see Tony Shipper from Fisher & Paykel here, and Tony will confirm that I had a reputation for disliking engineers. I don't know why, because they kept designing things I couldn't make, possibly, one of the reasons. And my figures as a manufacturing operations manager would go downhill every time a new design came in. And I was quite vocal on this, and John Bongard, who was the CEO at that time, said, listen, you Scots, in other words, go and help. If you can't do it, keep your mouth shut and go there and see what you can do about it. And I thought, easy. Easy. Lean manufacturing, let's take those principles, let's instill them into engineering, bit of discipline, few good metrics, and the problem will be solved. I failed miserably. Because you can't just transform the principles of lean manufacturing. Lean manufacturing is making sure you get the right goods and the right components to the right people in the right quality at the right time. The difference when you get into product development is not so much getting the goods there, but getting the knowledge there and making sure that that knowledge is verified and it's true, it's factual, it's not hearsay. So the whole difference between lean manufacturing and lean product development is making sure that you have the knowledge to be able to do what you have to do. And for that reason, we see product development in a different way, and we don't usually use the word lean. We like to use learning first. And learning first is making sure that you have the knowledge to proceed before you commit to design. And we'll begin with an observation and a question. The observation: it is uncommon for the companies we work with to truly know what the customers want. That's quite a significant statement. And if you dig a little bit deeper, they commonly do not know whether they can do what they think the customer wants. But they're working as fast as possible to do it anyway. Why is that? Now, this is not just New Zealand I'm talking about here. The associates we have with targeted convergence over in the US find the same situation. Now, I want to go into a little bit of product development history. There was a guy called Samuel Langley over in the US who was experimenting with unmanned flight. Now, Samuel was quite a clever guy, and he had a couple of gliders. One flew for half a mile and one flew for a mile. And Samuel had a great idea that he could have powered flight. And if he had powered flight, this would be a great benefit to the US war machine. So they gave him $50,000 to develop the first powered aircraft. So in 1898, he began full-scale development of this aircraft. Unfortunately, in 1902, he ran out of money, so they gave him another $20,000. And he designed his aircraft. He didn't want to pilot it though, and yes, it ended up in a crash. Meanwhile, in Dayton, Ohio, a couple of bicycle salesmen and a bicycle mechanic made the observation that while other investigators were spending thousands of hours designing their aircraft and about 5 seconds testing it before it crashed and killed them, they didn't believe this was a sensible approach. So they decided on experimentation. And Wilbur Wright said, we thought that some method could be found by which it would be possible to practice by the hour instead of by the second, there would be hope of advancing the solution to a very difficult problem without serious danger. and they began. What they did was they divided the problem of flight into three critical knowledge areas: lift, control, and propulsion. And they focused on each of those independently and nothing else until they had resolved all of the knowledge gaps within those three areas. And then they sent a cable to the family saying success is assured. Now, they hadn't designed an aircraft at this stage, but they knew they were going to be successful. And if you look at their part-time effort between May 1900 and December 1903, they found that the lift and drag calculations others were using were incorrect. They defined the optimum wing shape for control surfaces. They found out there was no engine capable of driving this aircraft. They invented the wind tunnel and mechanisms for measuring the lift and drag. They invented wing warping technology for controlling the plane in flight. The propeller they designed after they found the marine propeller wouldn't do the job. The propeller is actually 98% efficient even by today's standards. They also developed a lightweight aluminium engine, and they were virtually the fathers of the science of aeronautics. Now, if we compare the approaches, Langley had about 17 man-years. The Wright brothers, Orville and Wilbur, plus their mechanic from the bicycle shop, with their high school education, they spent about 22 months over 4 years. A friend, Langley, invested $70,000 of the government's money. The Wright brothers, $1,000 of their own money. So the Langley approach was to design, to build, to test, and then repeat. Design, build, test. The Wright brothers, they tested and experimented in the knowledge areas. They repeated that experimentation until they found a feasible solution. Then they designed their aircraft. Then they built it. And the difference, Langley's airplane never flew. The Wright brothers' first design was successful. Now, in 1997, the National Center for Manufacturing Science in the US had a survey, and they looked at 24 companies in the US, and they looked at the engineering productivity of those companies, found it was quite low. They looked at knowledge being shared across the projects within those companies, and it was ad hoc. They looked to see whether there were any unplanned design lookbacks in the system, and it was routine. Did they meet schedules? Almost never. And how about severe manufacturing startup problems? Almost always. So the product success variability was pretty high variability. After a decade of process improvements and the implementation of phase gate, etc., we found we got more gates, more checklists, more forms. We had value stream mapping, we had 5S, we had 3P, we had Six Sigma, quality function deployment, design automation, all of those tools that you all know about, and all very, very good and useful systems for improving quality. A decade later, in 2007, measured again. And there's an improvement. Percentage-wise, it was a pretty good improvement, but in the scale of things, it's still pretty low. And they found there was one company who were beating everyone else at this game, and that was Toyota. Very high engineering productivity, knowledge sharing, very few design lookbacks, maintaining schedules, very few startup problems, and the success was pretty high. So what's the state of product development today? Here's what we see. The details of the schedule and the requirements are set very, very early. Let's get them set because we better get on with this and get the job done. Set the concept very, very quickly, and then you set the tasks to meet the requirements. And this is phase gate plan, stage gate. And eventually, as you start going through those tasks, your critical knowledge gaps become apparent. Then the look-back start and continue for the life of the program. And the consistent result, project delays, cost overruns, engineers firefighting, and problems repeating on following projects. Now this will probably be quite familiar to all those people in here today. This is a typical product life cycle, and I'm sure that it's happening in your company right now. You get into the concept phase, you pick one, maybe two, start planning, get the design specs sorted out, get into the design phase, get your tooling built, no problems there, go straight through, test it, absolutely perfect first time, and then launch it. Manufacturing love it. Why couldn't you have designed this for us before? It's fantastic to build, and it's cheap, and it's good, and the quality's there, and the customers love it, and we make a profit. So that's the smooth, continuous flow, and the ideal product life cycle. That's happening in all your companies today, I believe. Or maybe it's more typical. A little bit of a look back here at the design phase. Then we test it, we've got to look back into design again. Then at the launch phase, we've still got some more problems that we find. Then at the production phase, it's happening again. And the knowledge of what is needed to be successful has not been learned at the early stages in this process, it's been learned at the late stages. And the result of this is look-backs cost companies a great amount of money. If you look back in the concept phase, the cost is minimal, but as you go through, when you get into the other phases, it becomes very, very expensive. You know, there's one there, if you look at the tool rework and scrap, I reckon that companies, or tooling companies in New Zealand, loved Fisher and Paykel in the 80s and 90s. They would build a plastics injection tool for 40 grand, knowing by the time it got into production with the reworks and the modifications, that tool would have netted them probably 200 grand, because the changes were there the whole time. Keep going, keep going, keep going. And we call this part where these decisions made, you know, sometimes known as the fuzzy front end, or maybe the land of little scrutiny. Start design early. Why? Because you need to finish on time. Choose fast and be specific, because we've got to get on with it and get it done. But what we're doing is we're making these decisions before you understand the customer needs, before technical feasibility is proven, and without knowing and applying lessons of why past products have failed or succeeded. And it gets worse, because what happens is when you get on to the next project, that knowledge is not flowing through. So what's product development trying to solve? Product development is about giving you a solution that meets your business goals, your profitability, satisfies your customer interests, and it's well within your technical capabilities. So what you're trying to do is find that sweet spot. That sweet spot is where you're going to be successful. So what do you need to do to find that sweet spot? You need to identify what the customer interests really are. Measurable, factual customer interests. Not things like, it's got to look nice, it's got to be bigger, it's got to be faster. Give the engineer something that he can design to. It must work at a speed of between this and this. Give them a range of values, factual values that they can actually design to. What's your technical capability? Can you build this successfully? Do you have the technology to be able to make it happen? Does that technology satisfy your customer interests? If you don't know these things, why are you going forward? That is what we've got to satisfy. Those knowledge gaps have got to be filled, and product development is all about learning how to close those gaps. And you do that by problem solving, focused study, experimentation, looking at the customer interests, looking at the design decisions for those customer interests, and also how design decisions interact with each other. If I change the material of a product, what does it do to the cost? What does it do to the corrosion resistance? What does it do to the metal forming or plastics injection molding? You've got to know, if I make a design decision, how is it going to affect other factors downstream? And when have you got to do it? Before you're committed to that design. Before your design decisions are committed. So what product development does, they don't make a product, they have the how-to knowledge of how that product is going to be built and performed. And let's just define what we mean by knowledge. Knowledge, facts, verifiable by objective, direct observation of testing. Knowledge that explains how and why things work. It's not opinion, it's not wishful thinking, it's not assumption, and it's not non-validated hypothesis. That knowledge must be validated and it must be visible. People you get an email that comes through, we have a problem. Let's have a meeting about it. Everybody's read the email, so you go in there and have the meeting, it's great. Does everybody see the same problem? I've got it in my head. Have you got it in yours? Are they the same? Can we share these? What does it look like? If we've got a picture, if we've got a diagram, if we can make it visible, then we can understand what we're talking about and we can come to a solution for the problem. When Toyota set out to design a product, how did they do it? The traditional way, specify as early as possible, make the design decisions as early as possible, let's test it to see if it works. The project management, have you finished? Are those drawings complete? Have you checked with the supplier? All task focused. And the innovation is on new product concepts. Toyota, rough targets to start, and let's evolve the details as we go through. Let's delay those decisions as long as we possibly can. What are the alternatives? A Toyota chief engineer was asked what his job was, and he stated, well, quite simply, it's to make decisions as late as possible, but not a second later. That's my job. The testing is mostly before the design to make sure you know what you're doing, to develop that knowledge. The project management is technical to manage the knowledge growth into those products, and the product breakthroughs are mostly the subsystems platforms. This is called design and test, and this is called test and design. So the Toyota philosophy is not about developing cars, it's about developing knowledge about cars, and great cars will result from that interaction. So if we look at the LFPD approach to product development, what we have is we have a knowledge value stream. And the product value streams pull the necessary knowledge to develop those successful products through set-based design, the design phase, validation, and launch. The work that the product development team are doing is in this knowledge value stream, making sure that knowledge is available, validated, and visible. And the knowledge is pulled through integrating events. You have the baseline knowledge that you start off with. You create new knowledge through set-based design. That knowledge integration goes with the product decisions. The learning and problem solving as you go through brings more knowledge back into that knowledge value stream, ensuring that you continuous reuse and continuous innovation in your knowledge. Project launch, the success assured point, is when you have a solution that's going to meet your product needs and your customer values. The knowledge and schedule are aligned throughout the project life cycle. First of all, you've got the business objectives. You have an integrating event. What are the business objectives? What are our profit targets? What are our EBIT requirements? What are our people What expenditure? What are we going to do here? Does engineering understand those customer interests? Define the alternatives to meet those customer interests. Define the capabilities that we have and the knowledge gaps. Decide which knowledge gaps we're going to fund and resolve. Close those gaps. Approve the project with scheduling and staffing. And at that stage, you know that the product launch is secure. Eliminate the weaker alternatives as you go through. Converge your design decisions, and you get the staggered transition into your detailed design. Capture that knowledge, and that's your base standard for your next project. What most companies are doing is the knowledge says they're here, but the schedule says they're up here. What they need to do are what are the key customer interests? What are the capabilities and the knowledge gaps? What are the alternatives and costs to pursue? Do you have solutions for those knowledge gaps? What are your integrating set-based decisions that you have to make? And if you know those, yes, you can go through. The learning first tools are simple, and you pull them through what we call PDCA. We grow knowledge through a process we call Lambda. I'll talk a little bit about Lambda as we go through today. That knowledge is then facilitated and it's documented in an A3. Talk a little bit more about that. Knowledge is visible through trade-off curves and limit curves, and that information is then pulled into knowledge reused through check sheets. So what is Lambda? Lambda was a phrase coined by a guy called Dr. Alan Ward, who worked with Toyota. And Toyota themselves wouldn't recognize the term Lambda. It was put together by Dr. Ward to try and describe the problem-solving process that the Toyota engineers used. And quite simply, Lambda is look. Go and see for yourself. That email, don't believe what it tells you. Get that visible knowledge. Go and have a look at exactly what's happening. Go to Gemba. Ask, what is the true cause of this situation? What are the causal factors? Let's model it. Let's make it as visual as possible so that we don't have any misunderstandings. And then let's discuss what we're finding. Let's reach consensus with knowledge and not opinion. And then let's take the action to verify the results and repeat. And what we can do is we can document that in an A3 report. Now, an A3 simply refers to the size of the paper. You can make it any size you like, really. But what it does is it pulls the story and it drives the Lambda discussion and consensus. And to be quite honest, the paper on this report is not important. It's the thinking that goes in behind it and how to prepare it. Here's an example. The TCC guys call them problem K-briefs. And the first thing you need to do is define the problem. What is the problem description? And this is very, very important because a lot of times you have very, very elegant solutions, but people have solved the wrong problem. So make sure that your problem description is there. And we also encourage a mentoring approach to A3s. What we found is that people see it as a report to sort of chuck through at the end of it and say, there you are, I finished the A3, how's that? The A3 grows as you go through that problem solving. And the mentoring approach would be for to bring your problem solver in and say, okay, what is the problem we're trying to solve here? Do we agree with it? Have we gone and had a look to see that this is exactly the situation we're talking about? What do we need to do? Some companies I've worked with in New Zealand have been looking for the A3. Joe, go and do an A3 on that and bring it back to me. Joe goes and does the A3, brings it back and says, that's not what I wanted. Go and do it again. Turns Joe off, and they've wasted a lot of time and a lot of money, and they're back into the rework and the relook. You start it by making sure that you know exactly what you're doing, and you go through each of those stages. You go through the problem description, the root cause, modelling it, alternative remedies, what the action plan is, how you're going to follow up, and did your results achieve the objective you set out here. And that's, the A3 is a very, very valuable document. Thinking is even more valuable. That was the learning part. Now we've got to capture it. And usually you capture these through the use of what we call trade-off or limit curves. And quite simply, a trade-off or limit curve, instead of taking a point-based solution and guess and test, does it work? Yes, fantastic, let's go with it. You test for 100% pass and 100% fail and all points in between. That gives you a limit curve. That is a fountain of knowledge for the designers in the future. If they're on the safe region of the curve, there's an infinite number of solutions to the problem. If they're on the infeasible region of the curve, don't bother going ahead. And you've got that information, that knowledge, you don't have to go and retest it again. If you need to move that curve for whatever reason, that's where your research and development work starts coming in. And Toyota used these limited trade-off curves to understand the technical situation, to communicate between specialties and functions, train new engineers, record knowledge, communicate between the customer and the supplier, conduct design reviews, communicate between developers and managers, and get the quality into the product. We actually run a workshop which is a full day of design of limit curves. So, don't have a lot of time here today. But what Dr. Alan Ward said was the most important thing he learned at Toyota was the dependence on and the power of those limited trade-off curves. He said they shared a lot of information with them, but they wouldn't share those limited trade-off curves. Now, the LFPD structure balances that system. You have the knowledge value stream, you have the product value stream. The knowledge value stream is knowledge of markets, customers, capabilities, technologies. The product development value stream is the bill of materials, manufacturing processes for producing that product. The functional managers own the knowledge value stream. Your electronics manager owns the electronic knowledge. Your sheet metal or tooling guy owns the knowledge there. And the chief engineer or project manager owns the product value stream. And there's a tension between those two. The chief engineer or the system engineer is saying, give me the technology I need to make this product. But prove to me that it works. I want to see that limit curve. I want to see that trade-off. I want to see your experimental results. I'm not going to take it at face value. If it's not ready, don't give it to me. It's not going to work. And the roles and responsibilities in this PDCA, everybody can solve problems. The functional managers mentor those people to ensure the success. And you establish and improve the resulting knowledge in check sheets. You review and innovate and teach with that knowledge. And the chief engineer pulls that knowledge into his project at the integrating events. And that knowledge is continuously flowing. So in summary, the LFPD system is about the knowledge value stream and the product value stream, the PDCA processing using Lambda, A3s, limited trade-off curves, and the check sheets, and the functional managers working on the knowledge value streams, and the chief engineer using that knowledge to enhance his product value stream. That's the balanced leadership. And in summary, that is LFPD. Probably taken me half an hour to put together what took months, years to put in place official practice, and Gallagher is able to share with you. I think it works. I wish I'd known about it earlier, because I think it does a great job.